Hey everyone, welcome back. So this will be part B of lecture 23. Now in the example we just looked at, we looked at this sequence. Right, we looked at this one. We just looked at this one. Right, now this term here, or this piece of the sequence, is -1 to the nth power. This is pretty much, you're going to see this a million times, but this is basically going to create kind of the oscillation of positive, negative, positive, negative, positive, negative, forever. And this is a really common thing to see in sequence definitions. And anytime you see it, you can just count on the fact that the sequence is going to oscillate across the zero line, right? Okay, and so sometimes, at times, it can be a little bit, it can add some additional confusion having this oscillation taking place, right? And so frequently, what we'll like to do when we have something like this is consider just the absolute value of the terms. Okay, so it's often useful to consider the absolute value of the sequence, especially when you're trying to determine convergence, and particularly when you're trying to determine convergence. So let's write that down. It is often useful to consider just the absolute value of the terms when trying to determine convergence, right? So fortunately, there's a nice little theorem here that tells us that this is a good idea to do, right? So theorem, let's say for the sequence A of n, if the limit of the absolute value of the sequence equals 0, then the limit of the sequence itself equals 0 as well. Okay, so if the limit of the absolute value equals 0, then the limit of the overall sequence equals 0 as well. Now, some ways this is kind of obvious, right? I mean, at first it could maybe not seem obvious, but if you really think about it, so let's say my sequence goes like this. Okay, right, so this is my sequence. So obviously these are all positive up here, and these are all negative down here. Okay, right? So if I take this same sequence and I just look at the absolute value, right, then what's going to happen, right? Basically, all I'm going to be left with is the top part, right? So this guy here would flip up to here. This guy here would flip up to here. This guy here would flip up to there, right? So you can see what would happen, right? You're just going to have the top value. Now, in a lot of cases, it may be easier to look at this sequence and say, oh, this converges to 0. And so what this is showing us, what this theorem is telling us, that if this converges to 0, then this one does as well. Okay, let's go ahead and actually prove this one, because I think this is, we kind of pick and choose what we prove in calculus courses because it's not really it's not a proof-based course, right? So we kind of pick and choose, and this is a nice one that kind of gives you some experience looking at proofs and thinking about them, but also is like accessible. Okay, so let's prove this. So let's consider, so we've got this base sequence A of n, right, which maybe has this oscillating characteristic, right? So let's consider the two sequences A of n, absolute value, and negative absolute value. Okay, so they're both, obviously the terms are the same. The a of n piece is the same, but here we're making every term in the sequence positive, and here we're making every term in the sequence negative. Okay, so what we're going to assume, and this is kind of the way the theorem is structured, it says that if the limit of the absolute value of a of n is equal to 0, so we're going to assume that that's true. We'll assume that a of n has a limit, the absolute value of a of n has a limit, and it's 0. Okay. Now, consider this. So recall this property of limits. Recall that the limit of c times a of n is just equal to c times the limit. Okay. So remember that. Remember that that's what that was a principle that we had, or a property that we had for limits. And so given that, we can clearly see then that the limit of negative absolute value of a of n will be 0 as well. Right? So it'll be, so in particular, the limit of the absolute value of a of n was 0, and so this limit should be -1 times 0, which is 0. Okay. All right. So that's good. Okay, and so then it should follow immediately from, basically the squeeze theorem, right? So you're going to have negative a of n, negative absolute value of a of n on one end. On the other end, you have the absolute value of a of n. And in between, you're just going to have a of n. And it's going to be between these values. Okay. All right. And so this is true for all n, obviously. And then it follows that a of n goes to 0 because these other two do. Right? So this goes to 0, that goes to 0, means that goes to 0 as well. Since it's between the greater than or equal, less than or equal then to these values. Okay? So kind of a simple little proof, but a nice one. I think it's kind of a nice one, and gives you some experience kind of thinking about these. So it's important to notice that, in the theorem that we just talked about, this is only true, well, it could be true when the limit is other than 0, but it's only true in general for sequences where the absolute value is equal to 0. Okay. So you could concoct example sequences where the absolute value of the sequence and the sequence itself have different limits. Right? But if the absolute value converges to 0, then the sequence itself must as well. Okay, very good. All right, so let's kind of shift gears a little bit here. One of the things that's very important when we start talking about sequences is kind of some of the pattern recognition that's required. Right, so sometimes the terms of a sequence are generated by some rule that does not explicitly identify the nth term of the sequence. Right, so let's write that down. Sometimes the terms of the sequence are generated by some rule that does not explicitly identify the nth term of the sequence. Right, and so when that's the case, it may fall on us to identify the nth term. And this can be tricky, nth term. That looks like scribble. Okay, and the nth term. Okay, so this can be tricky. right? So you get just given an arbitrary, just given some sequence that's generated by some rule, but we don't know what the rule is. It can be tricky at times identifying what that rule is. Let's do some examples. It's something that requires just a lot of practice actually to get good at. Some people are kind of naturally good at it. Some others require more experience, and some never get good at it. It sort of depends on who you are. But what about this one? So find the nth term of, now here's a bunch of terms in the sequence: 2 over 1, 4 over 3, 4 over 3, 8 over 5, 16 over 7, 32 over 9, and so on, right? So you're just kind of given the first, 5 terms and asked to find the nth term. So find the nth term of this, and we'll throw on here, determine if it converges. Okay, so it might converge, it might not converge, we don't know. Let's figure out what the nth term is. So this is kind of in general, this is sort of maybe how you want to think about it. Kind of look at the numerator and denominator separately in the case of a sequence like this. So note the numerators are all what? Powers of 2, right? Right, so this is 2 to the first, it's 2 squared, 2 cubed, 2 to the fourth, 2 to the 16th. So a good candidate for the numerator is 2 to the n. Right, so probably what's generating the sequence of numerators is 2 to the n. What about the denominator? The denominators. All right, what do we think might be happening there? Well, if you look at it, you can notice, right, the denominators are basically just the positive odd integers. Right, so they're just the positive odd integers. Right, so they're just 1, 3, 5, 7, 9, right, so on, 11. You can keep going, 13. Okay, so a good candidate there may be 2 to the n minus 1. Okay. Right, so that's a good candidate there. So one way we could write this sequence, I mean, we're only given the first 5 terms, so we have to infer that the pattern would hold, but one way to write this would be to say, that a of n is equal to 2 to the n over 2 times n minus 1. Right? That's going to produce the exact sequence that we just looked at, right? This will give us, the 2 to the n will give us what? 2, 4, 8, 16, and so on. The 2 to the n minus 2 times n minus 1 would give us, the odds: 1, 3, 5, 7. So we can reconstruct the sequence, using this as the nth term. So we'd say 2 to the n over 2n minus 1 is the nth term. Okay, now sometimes that can throw people, so let me just elaborate on what we mean by the nth term. Right, so if you can imagine, you've got 2 over 1, 4 over 3, 8 over 5, 16 over 7, dot, 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 and then somewhere out here you're going to have 2 to the n over 2n minus 1, dot, 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 right? So that's what we mean by the nth term, right? It kind of takes the generating principle behind the sequence and just explicitly writes it. But you can also think of it as, it's the nth term of the sequence, right? If n is equal to 2, you plug in a 2, you're going to get this guy. If n is equal to 3, you plug in a 3, you're going to get that one, right? So in general, this would be the nth term, whatever n happens to be. Okay, so the question then comes up, can we, does this sequence converge? Well, my guess is it probably does not converge, right? Like you can sort of look at it and say, well, this numerator is 2 raised to the nth power. That's going to get big pretty fast. This is just 2 times n. So that will grow, but not nearly at the rate of the numerator. So if you were to look at this, you could just kind of look at the top and bottom and separately and say, well, this is probably going to diverge because of how fast the numerator is going to grow relative to the denominator. But we could also kind of figure this out, right? So let's think of this as f of x equals 2 to the x over 2x minus 1. And, the limit there, what happens? Well, this is infinity over infinity, right? So we'll have to use L'Hopital's rule here, right? So we need the limit of the derivatives. And the derivative of 2 to the x is ln 2 times 2 to the x. And the derivative of 2x minus 1 is just 2. Okay, now can we evaluate this? Yeah, now we get a clear form. This is going to be, the numerator is going to grow without bound, the denominator is constant at 2, and so this limit will be infinity, right? So it'll be an infinite limit. And so that means a of n will diverge. Okay, so the sequence a of n will diverge. All right. Okay. Right, so the point of that example was to look at, just be able to think about how to derive the nth term. And as I say, this is a subtle art. There's a subtle art to this, and it's not easy. And depending, it's possible to make sequences up that are extremely complex that you would probably have a very difficult time figuring out. And one of the key things to notice about this is that many sequences begin the same, but have very different end behavior. Okay, so I'm using this term end behavior kind of from pre-calc, but let's take a couple of examples here, right? A couple of examples. So one sequence is this one, which we'll denote as a of n, right? We'll just say this is, so it starts out 1/2, 1/4, 1/8, 1/16, right? And this is one we've seen. This is 1 over 2 to the n. Okay, now this one we know goes to 0, right? This one converges to 0. So let's consider another sequence. It starts out exactly the same. So you've got 1/2, 1/4, 1/8, 1/15. And this one looks like this. This would be 6 over n plus 1 times n squared minus n plus 6. Okay, so the nth term here is very, very different. Even though the first 3 terms of the sequence are identical, you see in the 4th term it's 1/15 instead of 1/16. But this sequence also goes to 0 as n goes to infinity, right? So this one also converges it. So they look very different. The first couple of terms are identical. 4th term they start to differ, but ultimately they end up in the same place. Okay. What about this sequence? So here again, starting at 1/2, 1/4, 1/8, but then the 4th term is 7 over 62, right? And it continues. So this one looks like this, n squared minus 3n plus 3 over 6 times n squared plus 3n minus 2. Okay, so even though this start very much the same, right? If you were to take n equals 1, plug it into this, you'd get a half. If you take n equals 2, plug it in, you get a fourth, right? If you take n equals 4, you're going to plug that in, you get 7 over 62. So this sequence converges to 1/9. So as n goes to infinity, this sequence, the terms of this sequence get ever closer to 1/9. And then the last example, which I guess we'll call d of n, again starts out exactly the same, and then the fourth term is 0. Right, but it doesn't continue like that. If you were to plug in the fifth term, you'd find that it's non-zero. And this one is negative n times n plus 1 times n minus 4 over, oh sorry, this is actually supposed to be down here. So I'll write this one. This one was 9n squared minus 25n plus 18, right? So these are flipped. My apologies. So this one on this denominator is this sequence. This one, this sequence is this one on that denominator. So anyways, you can mess with that in a second. But this one, this sequence actually diverges. Right, this one grows without bound, it heads to infinity, which is not what you would expect just given the first 3 terms, right? Or the first 4 terms, really. You say, oh, okay, this is weird. It just kind of goes to 0 suddenly. But then the behavior is strange, right? Like these are not, they don't start out, they all start out the same, but they have very different end behavior. So it's instructive to think about that, you know, to recognize that these can be as complicated as you like, right? They can be as complicated. So C of n, right, is this. It's n squared minus 3n plus 3 over 9n squared minus 25n plus 18. That's a complicated nth term, right? dn, d of n, you know, that's negative n times n plus 1 times n minus 4 all over 6 times n squared plus 3n minus 2. That's a complicated nth term. They can certainly be more complicated, right? They can be as complicated as you like, right? But these two all start out the same. They have the identical first 3 terms, right? And then they start to behave differently. This one goes to 1/9. This one diverges. Okay, so that's what I mean. Like these are obviously examples where, you know, we were trying to find examples where the first 3 terms were identical, but then things kind of got wacky at term 4. Right, and so that's going to necessitate that you get some kind of weird expressions. But hopefully, this just kind of helps underscore the fact that, you know, sequences are not easy, and identifying nth terms can be a challenging task at times. Let's do another example. Find the nth term. Okay, so we're given negative 2 over 1. And then 8 over 2. And then negative 26 over 6. And then 80 over 24. And then negative 242 over 120. And so on, right? So this one kind of looks already like, ooh, yikes, right? Taking the numerators and denominators separately and just kind of thinking about this. What's going on in this numerator? Well, it's 2, 8, 26, 80, and 24. Okay. Now, one thing you might notice is that, you know, if you think about what is, you know, 3 to the nth, 3 to the n produces 3, right, 9, 27, 81, and 243, right? So you can see that these numerators, so this is like 3 to the first power minus 1. This is 3 squared minus 1, 3 to the third minus 1. So the numerator kind of looks like it's 3 to the n minus 1. Okay, so that's good. Now you can also see that there's some oscillation, negative, positive, negative, positive, negative. So somewhere in here is going to have to be a negative 1 to the n as well. You know, we can put that in the numerator, we can put it in the denominator, we can put it out front. So we're just kind of keeping track. We're going to need this for the numerator, we'll need that for the denominator, or sorry, this, you know, for the overall term. And then what about the denominator? What happens there? Well, it's what, 1, 2, 6, 24, 120. We did just recently discuss factorials, right? So you might recognize this as n factorial. So n factorial is, it's going to be basically 1, and then it's going to be 1 times 2, which is 2, and then it's going to be 1 times 2 times 3, which is 6, and then 1 times 2 times 3 times 4, which is 24, and then 120, and so on. Right, so it looks like the denominator here is n factorial. Okay, and so we could say that this sequence is 3 to the n minus 1. You know what, I'm going to write it slightly differently. Let's write it like this. We'll put the negative 1 to the n out front. Pardon me. And then 3 to the n power minus 1. And then n factorial. Okay, so this would be our sequence. That would be the nth term of our sequence. So not an easy, so these are not the most crazy, examples, but this is not this is something that requires some subtlety, right? You have to recognize some things. You have to recognize 3 to the n, for example. Really the way you'd have to come to this, you'd have to say, well, let's see, I don't see any obvious power of 2 thing going on here. What about powers of 3? Well, none of these are divisible by 3. So you might have to, it would be, there's a little bit of a stretch to get from up to here. You might just recognize that though, like 3, 9, 27, 81. Those numbers might be like firm enough in your head, and the fact that these are 1 less than them might spark some recognition, right? But you can see that this is a subtle activity, right? There's a lot of trial and error, a lot of kind of guesswork, hopefully recognizing some things, and then just having sort of a mathematical kind of worldliness, like knowing what 3 to the n looks like for the first 4 or 5 terms, knowing what n factorial looks like, knowing that the oscillating nature of the sequence will require negative 1 to the n be a part of it, etc. Okay, so that is another example, kind of a slightly trickier example. Okay, now we'll leave it at that. So that's a good example of finding an nth term. Okay, let's shift gears slightly and talk about something called monotonic sequences. So definition. A sequence, A of n, is monotonic if its terms are non-decreasing, right, like this. Basically, A1 is less than or equal to A2 is less than or equal to A3, right? So it's monotonic if its terms are non-decreasing, or we'll say non-increasing. So i.e. A1 would be greater than or equal to A2, greater than or equal to A3, and so on. Okay, so that's what we mean by monotonic, meaning it basically meaning that it just is going in one direction, right? It's either going, either the numbers are getting larger or the numbers are getting smaller, right? The terms of the sequence are getting larger or the terms of the sequence are getting smaller. Okay, so these are going to be very important, and we'll be using this going forward. Let's flesh out some examples of sequences and identify whether or not they are monotonic. Okay, so first example, what about this familiar one? Is this monotonic? No, right? Remember, this is 2, 4, 2, 4. Right, it just oscillates, goes back and forth. Right, so clearly it goes up, and then it goes down, and then it goes back up, and then it comes back down. right? So it's got both directions, right? So this is not monotonic. It oscillates. Okay. What about this guy? 2n divided by 1 plus n. Is this a monotonic sequence? Well, let's take a look at some of the values here. So you got a 1. When n is equal to 1, this is 2 over 2. Okay, and then when n is equal to 2, it's 4 over 3. And then it's 6 over 4. And then it's 8 over 5. And then it's 10 over 6. And so on. Okay. So it looks like the sequence is growing, right? It looks like it, right? This is, 1. This is 1 1/3. This is 1 1/2, right? So it kind of looks like things are growing, but how can we be sure? How can we be sure? It looks like it's growing, right? Growing only, i.e. getting larger. But how can we be sure? So what we'd want to be able to show in general is, let's call this B of n. We need to see that B of n is less than B of n plus 1. Right? If that were true, if we could somehow show that the nth term is less than the n plus 1 term, then that would guarantee that it's clearly growing, right? That the terms are getting larger. So can we do that? How can we do that? Well, we've got this very kind of clever way of doing that, right? So first we lay in the nth term, right, which we're given, 2n over 1 plus n. Okay, and let's just assume that this is true, right? Kind of cautiously assume it. And then plug in the n plus 1 term, 2n plus 1 over 1 plus n plus 1, right? And that'll be the bn plus 1, right? So hopefully that's clear, right? This is bn, right? So whatever n happens to be, you plug it in, you get the nth term. And this would give you the n plus 1 term. So whatever n is, this is one more. Okay? Now let's just do some algebra on this thing. Okay, let's just do a little bit of algebra, right? So this would be 2n over 1 plus n, and again, we're going to say that's less than 2n plus 2 over n, we'll say 2 plus n. Okay, so sorry, let's say 2 plus n here. Now we can cross multiply, right? And so we'll get 2n times 2 plus n should be less than 2n plus 2 times 1 plus n. All right. This is like getting, so that's just taking this, multiplying it up there, and multiplying both sides and doing the cancellation on the denominators. Okay, so then let's expand this, and I get, what do I get here? I get 4n plus 2n squared over here. And when I expand this, I kind of FOIL it out. I get what? I get 2 plus 4n plus 2n squared. All right, so I can kind of see here. So whatever this one is 2 more, right? So this is basically, if I can subtract this same value from both sides, and I get 0 is less than 2. Right, so that is true. But what does that tell us? Right? We started with the assumption that it's less than. Is this all reversible? Yes, this is reversible. Okay, that's the key, right? So this is a reversible method, right? So let's start with the fact that 0 is less than 2, and we'll derive the reverse. Right, so if 0 is less than 2, then it's certainly true that 0 plus 4n plus 2n squared is less than 2 plus 4n plus 2n squared. And that's going to be true, obviously, for all n. And we can do some factoring here. So I've got 2n times 2 plus n. That'll still be less than what I have over here, which is 1 plus n times 2n plus 2. Okay. Divide everything out, right? And I have, so if I divide both sides by 1 plus n, I get 2n times 2 plus n divided by 1 plus n is less than 2n plus 2. And if I divide both sides by n plus 2, I get 2n over 1 plus n is less than 2n plus 2 over 2 plus n, right? So these are just basic division rules. Now keep in mind here that all of these values are positive, right? The fact that I'm dividing by 1 plus n it doesn't change the inequality because it's a positive number, right? But if these were negative numbers, then this would not probably work for you. But just dividing by a positive doesn't flip the inequality or anything. So I'm good. And so, well, we're very close here. We've got 2n over 1 plus n is less than twice n plus 1 over 1 plus n plus 1, right? And this is just b of n, and this is b of n plus 1. Okay, so we've proven that for any two terms, n plus 1 are always, this relationship holds. Right, so this relationship holds. So that means that the sequence 2n over 1 plus n is monotonic increasing. Okay, so sometimes we say monotonic. Monotonic can be, there's kind of two flavors of monotonic. There's monotonic increasing, which is this case where the terms are always getting larger. And then there's monotonic decreasing, which is the case, the reverse, right? Where the terms successively are growing smaller. And this would be a monotonic increasing sequence. All right, and we just showed that just using this sort of argument. Okay, how about another example? We've got n squared over 2 to the nth minus 1. Okay, what does this look like? Is this a monotonic sequence? This will be 1, 4/3, 9/7, 16 over 15, and so on. Okay. Just kind of looking at these terms, like you may, sometimes you can sort of empirically determine whether or not the sequence is monotonic or not. Sometimes it requires a more elaborate argument. But just looking at these terms, right, if the fractions are throwing you off, you can just notice that you've got 1, and then 4/3 is 1.33, right? Okay, so 1 is less than 1.33. What is 9/7? Well, 9/7 is 1.286, right? So then it goes the other direction, right? So this one starts out at 1, and then it goes up, and then it comes back down. So automatically, this is not monotonic, right? It might be monotonic after this. We don't know, but you got a problem in the first three terms, right? Where 1 is less than 1.33, which is greater than 1.286. Right, so this one is less than this one, which is more than that one. So automatically not monotonic. Okay. Very good. Very good. All right. Excellent. So we're kind of getting towards the end. This is an extremely long section. A lot of stuff getting introduced here. But hopefully you're enjoying the material. It is kind of, it's a refreshing change. I mean, integration is great, derivatives are great, but this is just kind of an interesting, little of a step back and glancing down another avenue of mathematics. So let's define a bounded sequence. Okay, so sequence is bounded. Is it bounded? this is going to closely tie in with the idea of a limit. So first we'll say a sequence an is bounded above, okay, if there is an m, and this is a real number, not necessarily an integer. Could be an integer, but it's a real number. If there is so an is bounded above if there is an m, a real number m, such that an is less than or equal to m for all n. Okay, kind of an obvious, sort of simple definition, right? Like, let's say I've got a sequence that does this, right? And you can see it kind of flattens out. Well, somewhere up here I've got an m, right? And so you could clearly, easily say that if this is your a of n, then a of n is bounded above by m, right? Just means that all the terms of the sequence are less than m, right? So if my sequence heads towards some limit L, then clearly this value m is an upper bound. A of n is bounded above by m in this example. Okay, now, this is not a very interesting example. We'll get to more interesting examples for sure, but this just tells you, like, all this is saying is that m is some value, some real number that's larger than every term of the sequence. Okay, and then similarly, you could define a bounded below, a lower bound, right? So a sequence an is bounded below if there is some n in R such that a of n is greater than or equal to big N for all n. It's the same idea, right? I've got some limit L, and I've got a sequence that, maybe it comes down to L, and then there's going to be some m, right? And m is smaller than all the terms of the sequence. Turns out L is as well, right? So L will be these are both examples of lower bounds on a of n. L is going to be a special kind of lower bound, but m is also a lower bound, right? The key here is that the sequence is bounded. It doesn't continue to go down forever. Okay. All right. And then finally, we say that a sequence is bounded. So you've got bounded above, you've got bounded below, and a sequence is bounded if it is bounded above and below. Right? Okay, so there you've got different kind of levels of bound. You can be bounded above, you can be bounded below, or you can be both. Right? So that's all well and good. Okay, so what's the value of this bounded concept? Well, the value, let me flip pages here. The value is when you combine this idea of bounded and this idea of monotonic sequences. When you combine those two ideas, you get something kind of interesting. Okay, so we say if a sequence a of n is bounded and monotonic, then it must converge. Okay, so that's probably, I don't want to say that's obvious, but if you really understand what bounded means and you really understand what monotonic means, then this is sort of necessary, right? This kind of is necessary even without having some detailed proof, right? Bounded means there's, let's say bounded above, right? Bounded above means there's some real number for which all of the terms of a of n are less than. right? And let's say A of n is monotonic increasing. It means the sequence continues to go up forever. It never goes down. It only goes up or stays flat. But if it's bounded, it can't go up indefinitely. It has to sort of level off, seemingly, right? And so that's going to imply that it must converge, right? It can never go down. It can only go up. And if it's bounded above, it can't go up forever. It has to sort of curve into some kind of a limit trajectory. Okay, so let's see here. Let's draw a picture. All right, so let's say I've got L here, and the sequence kind of goes up like this. It's monotonic, right? It never goes back down. It's monotonic increasing. So that's going to imply that eventually it's going to hit some kind of a limit, and that limit will be, the limit of the sequence, right? So that's going to mean that the sequence converges. Right, so you can think of L as sort of the upper bound on this. Right, it's a special kind of upper bound. It's going to be called a least upper bound, which we'll get to in a moment. Right, so assuming L is a least upper bound, we haven't really formally defined that yet, then, clearly the sequence AN can only increase, but can never exceed L, then, L must be the limit of the sequence. Okay, so let's talk about this least upper bound idea. This is something that is a big opening concept in real analysis. So real numbers have an important property. Important property, right? And that property is usually termed completeness, right? So completeness, and that idea of the real numbers being incomplete is complicated, and it's really not it's more like an analysis topic again. But informally, what that means is that there are you can kind of say there's no holes or gaps between the numbers, right? So let's write that. Informally, this means that there are no holes or gaps, right? So the rational numbers, for example, are not complete, right? The rational numbers, so Q, the rational numbers are not complete, right? And there are many ways to construct examples of holes and gaps in the rational numbers, right? So like the square root of 2, for example, is an irrational number. And there are ways you can show that there is a hole or a gap if when you get to square root of 2, for example. But the real numbers don't have this problem. The real numbers truly are complete. There is no hole. There are no holes. There are no gaps. All numbers that are, it's a true continuum. Okay, and so when you get into real analysis, this kind of stuff. It becomes extremely profound. There's some really profound ideas that kind of come out of this completeness property, right? And so, and particularly contrasting Q and R is fascinating, right? There's some interesting stuff there, right? So you get into different sizes of infinity, for example, right? This is countably infinite. This is a different kind. This is a larger kind of infinite. This is uncountably infinite, right? And this all kind of stems from this property of completeness. Well, in a way, right? They're all kind of related. These are related ideas. But anyway, so completeness, the completeness property of the real numbers can be used to show that, if a sequence has an upper bound, then it must have a least upper bound, right? So completeness implies if a sequence has an upper bound, then it must have a least upper bound. Right? So a least upper bound is basically just an upper bound that is the smallest. Right? So in our example up here, for example, we said that L is the least upper bound. I said it, I didn't write it. But you can imagine there's lots of different upper bounds, right? There's M, and then there's another one above that, and there's an infinite number of them, isn't there? Right? Just keep going and going. But there's going to be one in particular, one value that is the least upper bound. Okay? And so that is, that idea of a least upper bound is an important idea in analysis, and it's going to be used, we're going to use it in the following proof as well, right? So the least upper bound property is important in the following proof. As I said, this is a key concept of real analysis, one you kind of pick up on first week of the course, you dig into it really in detail, and it's used everywhere in analysis. And a lot of the reason that calculus works the way it does is because of this completeness property of the real numbers and this least upper bound idea. But that's for another course. It's not for this course. But we are going to use the least upper bound property here in this coming theorem. So this theorem says if A of n is bounded and monotonic, then A of n converges. Okay, and so basically this is what this is kind of what we sort of discussed this already, right? We sort of brought this up. Like if a sequence is bounded and monotonic, then it converges. So let's prove it now. So let's prove it. Proof, right? So assume, what are we going to assume? Assume A of n is, well, we're going to just start by just saying it's monotonic increasing. Right? The argument will go very much the same for the monotonic decreasing case. We're just going to do this case though. Okay, so assume that, A of n is monotonic increasing, i.e. it's non-decreasing, it just goes up. Okay, so because A of n is bounded, there exists an upper bound m. Right, so what does that mean? Well, it's simple. It simply means that A1 is less than or equal to A2. It's less than or equal to A3, which is less than or equal to dot, dot, dot. AN less than or equal to dot, 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 less than or equal to M, right? Maybe that's too many terms to have to put in there, but you know what I'm saying. So basically, all of this, the terms continue to increase, and all of them are less than this value of M. Okay, now here's where we'll bring in the least upper bound, because, well, we should say from the completeness, the completeness of R, right? This is a big piece of it. From the completeness of R, there must exist a least upper bound. Right, and we'll call that L. The least upper bound, that'll be L. And so the picture is really more like this. A1 is less than or equal to A2, less than or equal to dot, 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 less than or equal to AN, less than or equal to dot, 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 less than or equal to L, which is itself less than M. Okay, so basically, you know, bounded gets us the m. The fact that we're dealing with real numbers means there's an L. Well, and I should say it's less than or equal to m, because m could be the least upper bound. We don't know, right? Okay, but at this point, the m is unimportant, right? What's important is the L. Okay, so all we've done right now so far is just kind of flesh out the relationship that exists between the terms of the sequence and this least upper bound L. Okay, so now for epsilon greater than 0, right? Epsilon is some positive value that's given. It's going to follow. It follows that, you know, if you take whatever L happens to be and you subtract off epsilon, then you're going to get a smaller number, right? Epsilon is a positive quantity. If I take L and I subtract a positive quantity from it, I'm going to have something smaller than L, right? Right. So L minus epsilon is less than L. Okay. And it also follows then, so for epsilon greater than 0, it follows that L minus epsilon is less than L, and, right, L minus epsilon is what? Is not an upper bound on the sequence. Now, what does that mean, that it's not an upper bound on the sequence? Well, what it means is that there's going to be some an, some values in the sequence, some terms in the sequence that are actually greater than this. Okay? And so, I mean, so consequently, we'll say, we'll say at least one. At least one term of an is greater than L minus epsilon. Right? The fact that L minus epsilon is not an upper bound on the sequence means that some term of the sequence is greater than it. Okay, that's kind of by definition. So, I mean, to write that a little more concisely, we might say L minus epsilon is less than A of n. We'll just denote it with a capital N, you know, for some n, for some natural number. Okay. All right. So that's good. So we basically have the situation now where we've got L minus epsilon is less than A of n, which is less than L. Right? So some term in the sequence is between L minus epsilon and L. Right? That's kind of logically what we've set up so far. Now, notice this. Right? Note that AN is monotone increasing. What does that mean? What does monotone increasing mean again, right? It means that all of the terms that come after A of big N here, they're all greater than or equal to this, right? So the sequence is monotone increasing, and from this it follows right, that A of big N is less than or equal to A of N for all N that come afterwards, for all N larger than N, right? So for all the terms after this, remember this is an infinite sequence, right? So for everything after A of N, this is smaller, right? This is less than or equal to everything that comes after it. Okay? Right, so we can sort of take this idea here and kind of and add some more quality to it, right? So what we can basically say, right? So it follows. So it follows that we've got our L minus epsilon, and that is less than A of N, right? Specifically because this is not an upper bound, and by definition, that just means that some terms of the sequence are larger than it. And that's what we have here. And because it's monotone increasing, this A of big N is going to be less than or equal to A of little n, right? Where little n is larger than n. And these are all less than or equal to this limit L, or sorry, this least upper bound L, which is, of course, less than L plus epsilon. We haven't said that yet, but that's obvious too, right? Right, epsilon is some positive quantity. If I add that to L, it's above it. And this is going to be true for all n greater than big N. Right, this inequality holds for all n greater than big N. Okay, so then clearly we can see that the absolute value of a to the a of little n minus L is less than epsilon for n greater than big N. Okay, right? Is that what we see here? So here's your L minus epsilon, here's L plus epsilon, right? Notice here you've got strict inequality, right? And so basically, if you were to start with this would expand out to a sub n less than L plus epsilon, a sub n greater than L minus epsilon. That's just kind of how you would expand this absolute value, right? So we've got this fact right here, right? And what is this? Well, this is the definition of convergence of a sequence. Okay, that's the definition. And this is for all epsilon greater than 0. Right? So epsilon greater than 0 was given at the beginning. Okay, so fantastic, right? So bounded and monotonic implies convergence. That's good. That's great. Let's do an example, and then we'll wrap this up. This one's been a very long lecture. Here we go. A of n equals 1 over n. Is monotonic decreasing? Right, this is 1 over 1, 1/2, 1/3, 1/4, right? These are fractions are getting smaller and smaller, aren't they? It goes to 0. It's monotonic decreasing, and it's clearly bounded below by 0. Right, so 0 would be a greatest lower bound. Right, it'd be the largest lower bound on this sequence. Another example. B to the n equals n squared over n plus 1. This is monotonic increasing. Right, that's clear, right? This is n squared, right? So whatever n happens to be, if it's 2, then this would be 2 squared, and this would just be 2 plus 1, right? So you're adding 1 to the denominator each time, and you're squaring the numerator, right? And so obviously the numerator is going to grow much faster, right? So this is monotonic increasing, meaning it never gets smaller, just gets larger. But is it bounded? It's not bounded. So it's monotonic increasing, but not bounded, right? So this is going to diverge. Bn goes to infinity is what I should say. Just diverges. What about this example? The good example. Cn equals -1 to the n. Well, definitely bounded, right? This is just -1, +1, -1, +1, -1, +1. It's definitely bounded above and below by 1 and -1. But it is not monotone, is it? Okay, so this one also does not converge. Okay. All right. Very good. I think that is where we can leave off. We covered a lot of material in this section. That's good. Next time, we will jump into infinite series. So this is going to be it's going to take the idea of a sequence and introduce the idea of adding all the terms of a sequence, and so that's what we call a series. And what happens when you add up an infinite number of of terms? Do you get a finite number? Do you get an infinite number? Do you get something else? We'll find out. So we'll see you all. We'll see you all next time. We'll see you all next time.